Hi everyone, I welcome you to the presentation of this video under DC biasing. So in the previous lecture, we were looking at a fixed bias configuration. This time around, we're going to look at another type of a configuration which we are calling the emitter bias configuration. So under emitter bias configuration, a transistor is biased in such a manner. As we know, transistors got three terminals: collector, base, and the emitter. So for emitter bias configuration, you have a resistor connected on the collector, which we are calling RC, and it has a current passing through it, which is IC, of course. And there is a resistor connected to the base, which we are calling RB, or base resistor. It's also excited by VCC, and it has a current passing through it, which we are calling IB. This time around, we are having a resistor connected on the emitter, and this resistor, we are calling it RE. So we have that one. Before going to the ground, you have a resistor connected to the emitter like that, which we're calling RE, and the current passing through it is IE. So this kind of a configuration is what we are calling the emitter bias configuration. So in the emitter bias configuration, we'll just do a treatment just like we did on the fixed bias configuration. You either take this route, derive the equation, and you take that route as well, derive the equation, and then you solve for all the unknowns. Okay, so we'll also take note of these formulas just like we did in the fixed bias. The emitter current is that collector current. It's given by those. VBE, which is the voltage in between base and emitter, is the difference between base and emitter, and it's 0.7. Then the voltage between between C and E, we are calling it VCE. It is the difference between the collector voltage and the emitter voltage. So let's start our analysis. So we'll start analyzing this configuration by taking this path. Okay, so with that path, of course, you're going to have those three terminals of a transistor. You've got VBE there, the voltage between base and emitter, and then you have VCC. From VCC, there will be a voltage drop on the base resistor, which we are calling RB. And then as it goes to the ground, it will pass through a resistor connected to the emitter, which is RE, which has the current code IE like that. So we have that, and then that's when it will go to the ground. So from here, we can derive an equation. We know that VCC, it will have a voltage drop there, which is IB RB, and then there will be a voltage drop there, which is VBE, and there's going to be a voltage drop there, which is IE RE. So if you write that in terms of an equation, this is the equation you have: VCC with a summation of those voltage drops. That's our first analysis. Then we can look at the second analysis, taking the path on the right. So you have a transistor with those terminals, of course, and then we have that. So this is just basically this part here, this side here, which is this one. So from this one, we can do our analysis. We know that our VCC, which is the supply voltage, it will have voltage drops. To have a voltage drop across the collector, which is that one, it's going to have a voltage drop across collector and emitter, which is VCE, and it will have a voltage drop across the emitter, which is IERE. That will produce that equation. Then we can solve. It's as easy as that. On this slide, we're looking at an example. The question is saying, determine the following for the emitter bias configuration shown. So this is the emitter bias. As you can see, there are two resistors, one on the base, one on the collector, and before going to the ground, there's a resistor connected to the emitter. Of course, there are capacitors. As I said, in DC analysis, we will not use capacitors, so you ignore capacitors. So let's try and calculate those parameters. So let's start our analysis with this path from VCC going there and then going to the ground. If we analyze it like that, okay, we have that. And then we are going to the ground like that. Okay, so with this, we said we derive our equation. This is the equation we had derived. VCC will have a voltage drop across the base, VBE, as well as on the emitter, having that. But the question is saying calculate IB. So from this one, we make IB the subject. So we know that IE is basically the summation of two currents, current in the base and current in the collector. So when you add those, okay, so we know that IE is basically the summation of two currents, IB and IC, which is just that. And then we want this whole equation to be in terms of one current, which is just IB. So we know we can express IC in terms of IB. We're going to have that because we know that IC is basically beta IB. The equation will be like that. So making IB the subject of the formula from this expression, this would further reduce to that. We've just factorized our IB there. Then making IB the subject of the formula, you're going to have that as the equation for IB. Then we have everything. Now we have VCC, which is 20. We have VBE, which is 0.7. I don't think it's a constant even if it's not given. RB we have start resistor in the base. RE we have is a resistor in the emitter. Beta we have, it's been given to be 50 in the question. So it's just plug and play now. When you substitute, you're going to have that as the current in the base. Then B is saying calculate IC. You know that IC is beta IB. We know our IB. Just substitute, you are going to have that as the IC. Okay, we continue. So for the other parameters, we can analyze it on the other path. With this one, we said we are going to have that as our equation. VCC having a voltage drop across the collector, across VCE, and across RE, which is IE. You have that. So with that, the question was saying calculate VCE. So from here, we make VCE the subject. You have VCC minus IC RC minus IE RE. So with that said, we know that for this path, our IC is the same current passing through RE, because the same current flowing like that current will come like that and then it will go down. So IC is equal to IE. So where there is IE there, we put IC. We have all these values. We know the value for IC, we know the value for RE and RC, and we know VCC. Just need to substitute there. When you put in the values, you're getting VCE as 13.97. Then the D part of the question was saying we calculate VC. So VC can come from this one. VCE is equal to VC minus VE. If you make VC the subject, taking this one going the other side, you have VCE plus VE. VCE, we know the value is this one. VE, it is the voltage on the emitter. The voltage on the emitter there is just basically the product of the current on the emitter and the resistor on the emitter. So you're going to have that. When you substitute those values, well, we know that emitter current and collector current are the same here. It's the same current flowing there. So when you do your substitutions, you're going to have that. You have 15.98 as the value for your VC. Then we have VE. VE saying it's a voltage on the emitter, which is basically IE and RE. And we are saying IC and IE, they are the same. It's the same current flowing there. So where there is IE, you put IC, you have that. Doing your substitutions, you're getting 2.01 as the voltage on the emitter. VBE is the voltage between the base and the emitter, and it's the difference between the base voltage and the emitter voltage. From there, the question was saying calculate VB. So making VB the subject, it's VBE plus VE. VBE is 0.7. VE is what we're from calculating there to be that. When you do your addition, you're getting 2.71 volts. Okay. And then G saying calculate VBC. VBC is basically the difference between the base voltage and the collector voltage. Base voltage is this one which we've calculated. Collector voltage is that one. When you do substitutions, you're going to get that as your VBC. So this marks the end of our analysis on the emitter bias configuration. Thanks for watching.